Hello guys, welcome to Electron, Millikan's oil drop experiment to find the charge of an electron and to prove the quantized nature of charge. So here, this is the figure of the Millikan's oil drop experiment. Now you don't need to go in depth with the detail for the apparatus or the setup, but I'll explain it anyways. So here first, the clock oil is well vaporized and then it condenses right here, and well the atomizer helps to reduce the oil into small tiny parts of oil, like small bits of oil, which goes through here and drops from this dome. Now here the x-ray helps to provide the friction for the oil drop in with respect to air, of course. And here the oil interacts with the air molecule such that it experiences viscosity. It experiences the resistance in air as viscosity. And here we use light and microscope to basically see the experiment. And here the double walled chamber has water running through it to maintain constant temperature. And here a positive plate, a positive signal and a negative signal is applied to the upper and bottom plate respectively, and the bottom plate is actually grounded, so there is only an positive force, a positive charge. Now here, during this experiment, there are two cases. First, when there is no electric field, the electric field supply or the electric field is cut off. So case 1, no electric field. In this condition, let's say this is the oil drop and here it goes down with weight W. Now the weight is given by mg, and we know mass is equals to density equals to mass by volume, so mass is equals to density into volume g, and the volume of this oil is spherical, so it is 4 by 3 pi r cube rho g, and the weight is balanced by the upthrust experienced on it, and here the terminal velocity goes downward as vt1, let's say. So that means the viscous force acts opposite to the terminal velocity, let's say it is f1v. And here the upthrust is the upthrust of the air molecules, the going upwards, which is the similar to this. The mass of the upthrust, or sorry, weight of the upthrust is 4 by 3 pi r cube sigma g, where sigma is the density of air, which is very small in respect to oil. So that means weight is equals to u plus f1v. And it's kind of unfortunate and sad, but I'll have to rub off some of the figure. So I'll do it from right here. So case 1, weight equals to u plus f1v. Now weight, which is 4 by 3 pi r cube rho g, is equals to 4 by 3 pi r cube sigma g plus the viscous force formula. If you know it, you know it. If you don't, it is 6 pi eta r terminal velocity 1. So we can take this to the right hand side and we'll get 4 by 3 pi r cube common. Rho minus sigma g is equals to 6 pi eta r terminal velocity 1. This is not dash, this is 1, okay? And here there are radiuses both sides. The radius, this cancels, giving us r square. Actually, we'll just keep it here. You know why? Let's say this is equation 1, which we will need for future purpose. And now we can do some very direct math. So here the pi cancels, as I said earlier, and here the r cube becomes r square, so this must be root under something. 3 multiplied 6, 18 by 4, 18 by 4, which is 9 by 2 eta. Eta is the coefficient of viscosity, I forgot to mention. Eta, and terminal velocity 1 by rho minus sigma g, right? This, that, yes. And now we'll be focusing on the case 2 part. So the case 2, that is when the electric field is on. Case 2, electric field applies and oil moves down, right? Oil goes down. So that means now the weight of the oil balances the upthrust, the electric field, and also the new viscous force. Now since there is an electric field, it travels with uh, another terminal velocity v2, so it experiences another viscous force F to v. So here weight equals to u plus Fe plus F to v, or 4 by 3 pi r cube rho g equals to 4 by 3 pi r cube sigma g plus, well, the electric force is the charge into the electric field, plus 6 pi eta r v to t. So we can take this common, 4 by 3 pi r cube rho minus sigma g equals to 6 pi eta r v to t plus qe. Now here using equation 1, which I rubbed out but I still remember, it is 6 pi eta r v1t equals to 6 pi eta r v2t plus qe. Now we're trying to find charge, and we can do some very quick math to get, well, this minus that. This is almost the same except for v1t and v2t, which we can take common. v1t minus v2t whole by the electric field. So in fact, I'll rub some of this out. In fact, this just becomes charge equals to 6 pi eta r v with terminal velocity 1 minus terminal velocity 2 whole by electric field. Therefore, charge is equals to, well, we find the relation or the equation for radius. So 6 pi eta v1t minus v2t by e multiplied by the square root of 9 by 2, the terminal velocity 1, eta also here, by rho minus sigma g. This is how we find the charge. Yes, this is it. 6 pi eta r, not eta, this is the radius, which is the radius, right? And here you can see that Millikan did this experiment many times and found the minimum charge to be 1.6 into 10 power minus 19 coulomb, which is the charge of one electron, and the other values as an integral multiple of this minimum charge. So that means Q is equals to Ne, where N equals to 1, 2, 3 and so on. So this proves the quantized nature of charge, and we have found the value of one electron itself. This is all for Millikan's oil drop experiment. But here are some notes. When we apply this electric field, if the oil goes up, in this equation what we do here is simply, instead of minus, we put plus. Now there's another case. If let's say that the electric field makes the oil stationary, that means it neither moves down or up. That means, well, there will be no velocity because it isn't moving. So therefore, there will be no viscous force acting on it. So simply 4 by 3 pi r cube rho g, so but this is sigma, I'll write it directly, is equals to qe, right? And here this will be if this is stationary, right? This is stationary, and if again we neglect sigma because it may be very small, then we'll just get charge into E, or let's divide it, 4 by 3 pi r cube rho g by E. This is if stationary and we neglect sigma, but this is not for the stationary case, this is going for the up case. If down, of course minus, which is the original equation. And this is it for Electron for modern physics. Thank you, and if you learned something, please like and subscribe.